So, as we have seen that the TCP has two phases. One we call it to be a slow start phase, and in the slow start phase the congestion window doubles after every round trip times. After every acknowledgement, the congestion window increases by 1. So, when the acknowledgement for all the packets transmitted during a window had come, then the window size actually gets doubled. So, this is what is called as the slow start phase. So, even though the increase is faster, but still we call it to be a slow start phase, because otherwise historically the TCP used to start the window from a window size equal to the receiver's advertised window size. So, in the slow start phase, the congestion window increases exponentially, and it increases exponentially till it reaches a window size which we call it to be a slow start threshold or a slow start threshold variable. So, it reaches the window size up to that, and after that the TCP goes into the congestion avoidance phase, and in the congestion avoidance phase we follow an additive increase and multiplicative decrease procedure. Now, however, in the slow start phase, if you are exponentially increasing the window size and if the TCP detects the packet loss, then again the window size drops to 1 and the TCP enters into a slow start phase again. Okay. However, if there is no packet loss and the window size increases up to the slow start threshold window size, and after that it enters into the congestion avoidance phase, then if the TCP detects the packet loss due to the triple duplicate acknowledgement, then the window size drops to half of the window size at which the packet loss is detected, and again the TCP enters into the congestion avoidance phase only. On the other hand, if the packet loss is detected due to the retransmission timeout, then the window size drops to 1 and the source enters again into the slow start phase, followed again by the congestion avoidance phase. But in the second case, that in the second time when it enters into the slow start phase, the value of the slow start threshold variable is set equal to half of the window size at which the packet loss was detected. Now, today what we will try to do is that we will try to analyze this slow start phase and the congestion avoidance phase and determine the throughput for such a TCP source with slow start phase and congestion avoidance phase in networks which have high bandwidth delay products. Right. So, there are certain assumptions. We will state these assumptions. So, the assumptions are we assume that we have an infinite data source. That means the source always has data to transmit. We also assume that there is a single bottleneck link. Single bottleneck link with capacity of mu packets per second. We assume that the bottleneck buffer size is B and the propagation delay tau I are taken to be deterministic. Right. So, what we are assuming is that there is a single data source. Okay. So, the one data source and there is one receiver, and in the network there is one bottleneck node. We assume a single bottleneck node, and that bottleneck node has a buffer capacity of B, and the node serves the packet with a rate of mu packets per second. Okay, and the propagation delay tau, okay, the propagation delay tau, that is assumed to be constant. Okay, so this we call it to be, so let us say tau. So if we define the window evolution, so let us define the normalized buffer size. So the normalized buffer size beta is defined to be B upon mu tau plus 1. Okay, so this is the normalized buffer size. So let us define T to be equal to tau plus 1 upon mu, right. So now this is the propagation delay, and this is the service time. So this is the total round trip time. So tau therefore denotes the round trip time. Okay, so this I can write to be B upon mu T. Okay, now mu is the service rate, T is the round trip time. So therefore, so this is the delay. Okay, and this is the bandwidth. Okay, so if B is less than or equal, beta is less than or equal to 1, that means we have the case of large bandwidth delay product. Essentially it means that the bandwidth delay product, so this is what is called as the bandwidth into delay product, this mu T is greater than or equal to the bottleneck buffer size. So we would like to analyze the situation or the throughput characteristics of a TCP source in networks which are having large bandwidth delay products. By large bandwidth delay products, we say that the product of the bandwidth into the delay, and where the delay happens to be the sum of the propagation delays plus the service time, that is greater than or equal to the buffer size, that is greater than the bottleneck buffer capacity. Okay. Now let us try to therefore analyze such networks which are having large bandwidth delay products. So the analysis of such networks which are having large bandwidth delay products. Now the maximum window size that can be there, so we call it to be the W pipe, the maximum window size, or W max, will be mu T plus P. Now this many number of packets can be there in the transit, and these many number of packets that can be stored in the buffer. So this is sort of the maximum buffer size, the maximum window size. This indicates what can be the maximum window size in the network, right. That is, the maximum window size actually denotes what is the maximum number of unacknowledged packets that can be there in the network. Now the maximum number of unacknowledged packet that can be there in the network is equal to the number of packets that can be there in the transit plus the number of packets that are actually queued up in the buffer. Okay, so mu T plus B actually indicates the maximum number of unacknowledged packets that can be there in the networks, and therefore by definition it will be the maximum window size. Now let us try to see how the window evolution takes place during the slow start phase. The things will become then clearer. So the situation is something like this, that there is a source, we got a bottleneck buffer of size B, and this is serving at a rate of mu packets per source, and we have the propagation delay of tau, and this serves packets at the rate of mu packets per second, and this is a destinations, and the propagation delay is tau. So this model actually is a very simplified model of the TCP connection between a source and a destination in a large bandwidth networks. So now let us try. So our assumption is that a source is always data to send, therefore it is an infinite data source. Our assumption is also that the propagation delay is assumed to be constant. Usually in practice the propagation delay may not be constant, but it is assumed to be constant here, okay. And there is only one single bottleneck node, and then that bottleneck node has a capacity of holding B packets, and it has a service rate of mu packets per second. So now let us try to see how the window evolution takes place during the slow start phase. Now the window evolution that takes place in the slow start phase is something like this. That let us say time, the packet which has been ACKed, window size, packet number, and then queue length. Now if you see at time 0, window size is 1 in the slow start phase. So we release the packet number 1, and the queue length, that packet will go into this buffer, right. This packet will go directly into the buffer when the packet number 1 is released, and it will sit here, and then the queue length will be 1. Now after t time unit interval at time t, right. Now note that this t here consists of tau plus 1 upon mu, that is the propagation delay plus the service time. So when this packet 1 has been released here, okay, after the time t, the packet that has been acknowledged will be the packet number 1, and when this packet is acknowledged, the window size becomes 2, and then we will release the packet 2 and 3 that will be released, okay, and these two packets will go into the buffer and sit there, right. So now what is happening during the slow start phase? Initially we start from the window size equal to 1. We release that packet. When that packet's acknowledgement comes back after a round trip time, and that is denoted by capital T here, when the packet's acknowledgement comes back after the round trip time, the window size now doubles. So the window size becomes 2, okay. The window size, for every acknowledgement, the window size increases by 1 in the slow start phase. So when this particular packet's acknowledgement comes back, the window size becomes 2. So we release now the 2 packets, these 2 packets go and sit into the buffer. Now if you see the packet number 2 which was released earlier, okay, in this case, the packet number 2, when that gets serviced after a time interval of t, that means at time 2t, the packet which will get at 2, okay. Now when this packet comes here, the 3 actually starts getting service, okay. So the window size now becomes, when the packet number 2 has been acknowledged, the window size becomes 3. Already 3 is there in the transit, right, and therefore we can now release the packet number 4 and 5, and since C3 is there in the transit, these two packets will go and sit into the buffer, and therefore the queue length is again 2. Now the packet number 3 will, the acknowledgement for packet number 3 will come back to the source after another interval of 1 upon mu, because the difference between 2 and 3 will be 1 upon mu, where 1 upon mu is a service time. The packet that gets acknowledged is 3, alright, and when the packet that gets acknowledged is 3, the window size becomes 4. Now when the window size becomes 4, now at this point, when 3 was in the transit, okay, the packet number 4 was getting served, okay, and since the window size is 4, packet number 5 is already there in the buffer, we can release packet number 6 and 7, okay. So therefore 5, 6, 7 will be there in the queue, so the queue length is 3, 4 will be there in the transit, and therefore the total window size is 4, and that indicates the maximum number of unacknowledged data that can be there in the transit. Now similarly at 3t, okay, and the 3t, okay, at time 3t, okay, we now get the acknowledgement from the packet number 4, which was released at time 2t, and then the window size becomes 5, and now the packet that will be released will be 8 and 9, and these 8 and 9 packets will go and sit into the buffer. Note that the packet 5, 6, 7, they are there in the transit, okay, 5, 6. So therefore at 3t plus 1 by mu, you get the packet which is acknowledged is 5, the window size becomes 6, the packet that are released are 10 and 11, and then the queue length becomes 3. Note that in the queue the packet number 9, 10, 11 will be there, and packet 6, 7, 8 are there in the transit, and then they will get acknowledged here. So we'll have 3t plus 2 by mu, where we get the packet number 6 acknowledged, the window size becomes 7, and we release the packet number 12 and 13, and the queue length becomes 4, okay. Similarly we get after 3t plus 3 by mu, and 3t plus 3 by mu will get the acknowledgement for 7, and then the window size will become 8, and 8 we will release the packet number 14 and 15, because note that there are already 4 packets in the queue and 3 packets in the transit, okay. So therefore the window size in that case becomes 5, okay, and so on. Now at 4 by mu, 4 by mu is essentially nothing but the 4t, and at this point we will receive the acknowledgement of 8 here, okay. So this way the evolution of the window takes place in the slow start phase, and as you can see from this example that the window is essentially evolving in an exponential manner during the slow start phase, right. So you can see here at the time 4t, the acknowledgement for 8 comes, the window size becomes 9, and you will acknowledge packet number 16 and 17. So the window size is 9, the acknowledgement for packet number 8 has come, and note that all the packets, that is 9, 10, 11, 12, 13, 14, they are all in the transit, and therefore the queue length again will be 2, okay. So therefore this illustrates the exponential nature of the window evolution. Now let us define each of these, that is t and this interval and this interval, to be the mini cycles, okay. So we define the ith mini cycle to be denoted by it into, so this indicates our ith mini cycle. Now let us say that wt denotes the window evolution window size at time t. Okay. Now, if you see here, if you observe the behavior here, so this is the first minicycle, the second minicycle, the third minicycle, the fourth minicycle, and so on. So, if you see that in n plus 1th minicycle, in n plus 1th minicycle, the window size W is nt plus t plus m by mu. So, the window size at nt plus t plus m by mu is given by 2 raised to power n plus m plus 1 for m lying between 2 raised to power n minus 1 and 0. Or in other words, if you see in nth minicycle, it will be W nt plus m by mu, which will be equal to 2 raised to power n minus 1 plus m plus 1 for m lying between 2 raised to power n minus 1 and 0. So, as you can see here, let us say that if you have n is equal to 3, if you keep n is equal to 3 here, and then if m is 0, okay, the window size is 3 minus 1, 2 raised to power 2, that is 4 plus 1, that is 5 here. If you take now 3t plus 1 by mu, that is m is 1, then it becomes equal to 5 plus 1, that is 6 here, and so on. All right. So, this way you can determine what will be the minicycles, okay, the window size at the nth minicycle. Similarly, the Q size, the Q length during the nth minicycle is given by Q of nt plus m by mu will be equal to m plus 2, again for m lying between 0 to 2 raised to power n minus 1. So, this is the Q length. Now, if you see from here in the nth minicycle, the maximum window size will be when m achieves a value of 2 raised to power n minus 1, and that will be 2 raised to power n. So, as you can see here that in nth minicycle, the maximum window size W max will be equal to 2 raised to power n. Okay. And similarly, the maximum Q length, if you want to know, then you have Q max, which again if you put m is equal to 2 raised to power n minus 1, we will have 2 raised to power n minus 1 minus 1 plus 2, which is equal to 2 raised to power n minus 1 plus 1, which we can approximate to be equal to 2 raised to power n minus 1. So, if you see from here that the Q max is approximately equal to W max by 2, the Q max is approximately half of the maximum window size, which will become clearer from this example here. As you can see here that the maximum window size in this minicycle is 8, and half of 8 is 4, which is approximately equal to the maximum Q length, which is actually here 5, right. So as we have seen, that the slow start, during the slow start phase, the window increases in an exponential fashion, and we can write an expression for the window size evolution as well as the queue length evolutions. And we have also seen that the maximum queue size, that is the maximum queue size, will be approximately equal to half of the maximum window size in the nth mini cycle. Right. Now let us do one thing, that let us define some variable called NB. Okay. So let us say that define NB such that define NB such that 2 raised to power NB minus 1 plus 1 is less than B, that is B is the buffer size, but but the B itself is less than or equal to 2 raised to power NB plus 1. So we choose an NB such that the 2 raised to power NB plus 1 is greater than or equal to the buffer size, but 2 raised to power NB minus 1, okay, plus 1 is less than the buffer size, right. So we have chosen some number NB such that this relationship holds good. Now in, let us say, NBth mini cycle, right, what will be the Q max? If you see from our expression for the Q max, that is the maximum Q length, the maximum Q length will be equal to 2 raised to power NB minus 1 plus 1, okay. So it will be 2 raised to power NB minus 1 plus 1, but since this is less than B, no buffer overflow will take place. In NBth mini cycle, right. So what we are saying is that choose some number NB such that 2 raised to power NB minus 1, that is plus 1, this the buffer size B lies between these two quantities. So if you now take NBth mini cycle, if I now take NBth mini cycle, we know that in NBth mini cycle the maximum Q length will reach 2 raised to power NB minus 1 plus 1. Now since by our assumption this quantity is less than the buffer size, no buffer overflow will take place in the NBth mini cycle. However, since 2 raised to power NB plus 1, which is going to be the maximum Q length in the NB plus 1th mini cycle, the buffer overflow can occur in the NBth plus 1 mini cycle. So since 2 raised to power NB plus 1, which is equal to Q max in NB plus 1th mini cycle is greater than or equal to B, buffer overflow will occur in NB plus 1th mini cycle. Right. Now the question really is that, note that the maximum Q length which is going to be there in NB plus 1th mini cycle is greater than or equal to B. So that is the maximum Q length, but the Q length can become, the buffer can fall short of the Q length somewhere in between also during the NB plus 1th mini cycle. So we need to determine at what point the Q length exceeds the maximum buffer size. So therefore during this cycle, okay, the Q length will exceed, okay, the buffer size for that value of M, for which, so this is the Q length in at B plus 1th mini cycle, and this in general is given by an expressions for M plus 2, and whenever that becomes equal to B plus 1, okay, if it becomes equal to, buffer overflow will occur. So therefore, m should be equal to b minus 1. Okay. So at this point, right, m equal to b minus 1, the buffer overflow is occurs. So for this situation, the window size is call it to be WB, which is given by W of NBT plus T plus m by mu, and if I keep m equal to b minus 1, so now actually this is equal to 2 raised to power nb plus m plus 1, which becomes equal to 2 raised to power nb plus b. Right. So you can see here from this situation, because we have an expression for the Q length variations, in the nth mini in nb plus 1th mini cycle is given by 2 raised to power n plus m plus 1, and that is what we have written here, 2 raised to power nb plus m plus 1, which is given by 2 raised to power nb plus b. Now, since by definition our buffer b is less than or equal to 2 raised to power nb plus 1 and b is greater than 2 raised to power nb minus 1 plus 1, we can approximate the WB to be equal to 2b. Okay, it's approximated to be equal to 2b. Now note that, now what is happening? Let's see that the window evolution during the slow start phase is exponential. That's what we have seen, and we have argued that the buffer will overflow in the nb plus 1th mini cycle if the Q length exceeds the buffer size and the window size reaches approximately equal to 2b. So when the window size reaches approximately equal to 2b, the buffer overflow will occur. Now the thing is, this to happen, that the buffer overflow should occur in the slow start phase, this maximum window size, that is W, should be less than or equal to the slow start threshold, because if it is not less than or equal to the slow start threshold, then actually the slow start threshold itself would have passed. Okay, so the buffer overflow occurs during a slow start phase only if WB is less than or equal to WT, which is slow start threshold. And WB is the max window size at which buffer overflow so this, if this window size WB is less than or equal to the slow start threshold, then only the buffer overflow will occur during the slow start phase. At least what we are trying to say is that a slow start phase should last. Now the question is how we have chosen the slow start threshold, that is WT, right? So now let us see how we have chosen WT. Now note that the maximum window size that can be there, W max, can be mu t plus b. This was our W pipe, right? Because this is the bottleneck buffer size, so that this denotes the maximum number of packets that can be there in the buffer, and mu t denotes the maximum number of packets that can be there in the transit. So therefore mu t plus b is the maximum window size that can be there for this source destination pair, which has the bottlenecks, which has a single bottleneck node with a link capacity of mu and the buffer size of b. So mu t plus b can be the maximum window size for this source destination pair. So this is the maximum window size, and typically we will set the slow start threshold Wt to be half of this, that is W pi by 2, and that we will keep it to be equal to mu t plus b by 2, and which denotes to be equal to 1 plus beta mu t upon 2, which if we write this expression in terms of beta. Now Wb we have written to be equal to 2b, which we can approximate to be equal to 2b into, which is equal to 2 twice of beta into mu t. That means a buffer overflow will occur during a slow start phase buffer overflow occurs during a slow start phase if twice of beta mu t is less than or equal to 1 plus beta mu t by 2, which implies that beta should be less than or equal to 1 by 3. So what it is trying to say is that if the beta, that is a normalized buffer size, if it is less than or equal to 0.33, then the buffer overflow can occur during a slow start phase. That means the packet can be lost during the slow start phase. Okay. Now one thing, if the packet is lost during the slow start phase, then two things happens. Whenever the source detects that a packet loss has occurred, it drops the window size to w equal to 1 and enters into another slow start phase, right? It enters into another slow start phase. Now when it enters into another slow start phase, this time the slow start threshold variable will not be the original slow start threshold variable which was used in the previous slow start phase. That will not be, but it will be half of that, because whenever you detect a packet loss, you set your slow start threshold variable equal to half of window size at which the packet loss has been detected, right? Now let us try to therefore analyze what will be the throughput of this TCP connection in the slow start phase. Okay, so we now try to determine the throughput in the slow start phase. Now in this case we consider two cases. In case 1, we assume that no buffer overflow occurs during slow start phase. Now if you assume that no buffer overflow occurs during slow start phase, that means Wb at which we are saying that a buffer overflow can occur should be greater than the slow start threshold variable, right? If it is greater than the slow start threshold variable, then what happens? Our window size increases to the slow start threshold, and after that the TCP enters into the congestion avoidance phase, right? So therefore now, so that slow start phase, the clean slow start phase, there is no buffer overflow. Another, we consider another case where the buffer overflow occurs during the slow start phase. So we consider two cases. Case 1, we consider that no buffer overflow occurs during slow start phase. That means this case corresponds to the situation of WB is greater than WT. Case 2, we assume that buffer overflow occurs during slow start phase. That means WB is less than or equal to WT. Now, in the case 2 situation where the buffer overflow occurs during the slow start phase, there will be 2 slow start phase. Now, we need to consider 2 slow start phase. In one slow start phase, what will happen? Our window size increases to WB, at which the buffer overflow occurs. The window drops to W equal to 1 and again enters into the slow start phase, right? But this time it will not go to WT, it will go to WT, but this WT will be different than the previous slow start phase WT, right? It will be equal to half of the window size at which the packet loss has been detected. Now let us try to therefore determine throughputs of the slow start phase in both the cases. So we consider the case 1 first. So case 1 is that WB is greater than the slow start threshold. Okay. Now in this case the slow start phase ends when the window size reaches WT. Now we will approximate the window evolution during the slow start phase to be equal to 2 raised to power t by t. Now note that the window is increasing actually in a discrete fashion as we had seen, and we had seen that the window evolution is actually given by W, in the nth mini cycle W n t plus m by mu by this expression. Now we can actually have a continuous time approximation of this, and we can say that a window evolution is given by W t by t. Now let us say that T1 is T1s slow start threshold denotes the duration of this slow start phase, then this will be equal to t times log 2 of WT, right? The slow start phase will end when the window size has reached WT. Similarly, let N1s denotes the number of packets transmitted during the slow start phase. And now the number of packets transmitted during the slow start phase, if you see the window evolution, approximately equal to the window size. I mean, if you can see the evolution of the window size here, let me just show you the evolution of the window size. That will clearly tell you that as you can see from here, that the number of packets transmitted during the slow start phase, number of packets successfully transmitted during the slow start phase is approximately equal to the window size. So the number of packets successfully transmitted will be approximately equal to the WT, right? Now we consider the case 2. Case 2 is when the WB is less than or equal to WT. So therefore buffer overflow occurs. Buffer overflow occurs during the slow start phase. So the buffer overflow occurs during this slow start phase. This is followed by another slow start phase. Right. So the buffer overflow which occurs during the first slow start phase, this will be followed by another slow start phase. So now let us try to analyze the throughputs in both phases. So first phase we will consider, okay. So the first phase of the slow start phase. In this case, we can assume that the threshold which we have kept to be equal to W max by 2, and that we have kept equal to B plus mu t by t. Now when the window it reaches the WT, that is a slow start threshold, when it reaches WB, that is the window size at which the buffer overflow occurs, right. So now let us determine the time to reach, okay, the T11s, I say the time for WT to reach window size W, at which point, okay, the buffer overflow occurs, plus the time to detect the packet loss. And this is equal, and this will be the duration of the slow start phase, right. This will be the duration of the first phase of this slow start phase. So this is given by T of log WB plus T. So by following the same evolution, you know, that WT is equal to 2 raised to power T by T. So the time it takes for WT to reach WB will be equal to, you know, T into log of WB, plus it takes another round trip time to detect the packet loss. So therefore, you know, we add another T. So as a result, you know, this time is given by log of WB plus 1. Now again, the window size has reached up to WB, right. The window size is WB. So the total number of packets which have been successfully transmitted can again be approximated by WB. So we will say that, let us denote, let's denote N11s to be equal to number of packets successfully transmitted, and this is given by W, right. So what we are saying is that we are assuming a condition where the buffer overflow occurs during the slow start phase, right. So this is the first phase of the slow start phase. Now the packet loss is detected, okay. When the packet loss is detected, that time the window will drop to W by 1 and another slow start phase begins. So now let us consider the second phase. Now in the second phase, note that the slow start threshold variable WT, which was earlier set in the initial condition, which was set equal to W max by 2, it will not be that. It will be the half of, it will be set equal to half of the window size at which the packet loss was detected. It can be shown that the window size at which the packet loss was detected that the window size at the time of packet loss detection is actually given by minimum of 2w minus 2 into the original Wt which was there. So, the new Wt will be set equal to minimum of Wb minus 1 into Wt by 2. And what was Wt by 2? It was W max by 2, so that will be actually equal to minimum of Wb minus 1 into W max by 4. Now, we will now determine that. So, now when the window size reaches this new Wt, the slow start phase ends and a congestion avoidance phase begins. So, we will now determine how much time it takes for the source to remain in this phase, okay, and the number of packets that it has successfully transmitted. So, which in our case will be given by T1 2s to be equal to time for Wt to reach this new slow start threshold, which is given by the T of log of the new slow start threshold, which is Wb by 1 and W max, and the number of packets successfully transmitted N12 is given by the window equal to is given by this. So therefore, we got two phases. We can determine how much is the time for the slow start phase cycle, and we can also then determine how much is the maximum number of packets that has been transmitted during this slow start phase. And from this we can determine the throughput for the slow start phase. Okay. So now we will go into determining the throughput for the congestion avoidance phase.